Organizing team, please stand up, those who are here, which is everybody except Ji Woo. Have Stephen Terrio, Ruth Charney, Ron Levy, and Tony Bari. And Ji Woo, who could not be here, has visa problems. So welcome to all of our organizers. Oh, we have somebody here from the Fields Institute. No, we don't. Okay. So we do, in fact, have someone from the Fields Institute. Okay. So.
Good morning. My name is Kirsten Vanstone. I'm the head of operations at the Fields Institute, neither a director nor deputy director. Deputy director is just in a meeting this morning. And Deirdre Haskell, our director, is working from home today. So I would bring their greetings, however. We're delighted to have you here. I see lots of familiar faces. And just a quick idea for me, since I have to look at all of the numbers for the Fields Institute. Is anybody visiting us for the first time today? Excellent. Oh, wow. So many of you are second timers. Or not, or third or fourth, or many, many more. All right, excellent. Well, if you're here for the very first time, welcome. Thank you so much for coming. I am delighted to put on the lovely weather from Toronto for you. Yeah, we do our best, but that's one thing we cannot control. If you have any questions about things at the Fields Institute, please feel free to come and ask me or any of my colleagues, Shane or Shuchen, who are here today. We'll have, if you're not familiar with the building, I like to just let you know that the exits are many-fold, but if anything happens like a fire alarm, the closest to this room is just behind us over here, but there are stairs for that. If you need any assistance, one of us can help you get down those if needed. If we have a fire alarm, please do exit as soon as it goes off. I am also the health and safety person, so I feel I have to announce such things. And that's the boring part of the Fields Institute. The more exciting part of the Fields Institute is we've been around for more than 30 years now and have been really enjoying being a community hub for mathematicians from all around the world. And it is exciting. I know I look at the names on the list of people who are speaking today and see people in the audience to know how many countries are represented today. And we are delighted to welcome you here to Toronto. So with that, I don't think there's anything else I have useful to say. So I'm going to hand it back to Paul. Please have an enjoyable and productive workshop.
So the only thing I have left to add is she mentioned the weather, and you may notice that it's been our experience that the weather inside this room is inversely proportional to the weather outside. So we could hope that it doesn't get too warm outside so that we won't all freeze here, because we have had some problems with that, and apparently they don't have any control over this. So there's nothing we can do about it. So we hope it's not too warm outside and then we won't freeze. Anyway. Now I'll introduce Larry Taylor, who's going to host the first session.
Well, excuse me. You've all been welcomed more than once already, and we're already running just a little bit late. So I would like to introduce Alejandro Adem, stable splittings for spaces of commuting matrices. Take it away.
Thank you. Thank you very much. You can all hear me. Okay. So it's a real pleasure to be here. For those of you who aren't from Canada, welcome to Canada. The Fields Institute is definitely a great place, as are all the math institutes in Canada. And I love them all equally. I want to say that clearly. And some of you will understand why. We do have a former director here in the audience, Ian Hamble. So first, I want to say, start by, first of all, mentioning that the main piece of work I'm going to talk about is joint with Simon Grishacher and Jose Manuel Gomez, and it's in a paper that was recently published. But before I jump into the mathematics, I want to say something about Fred. So I first met Fred around 1981, and first I'll say that as a person, he's a wonderful person. He was also a great friend, and in my opinion, exceptionally talented, as well as generous. So I met him when I was an undergraduate, and we literally had hundreds of conversations many times the same conversation over and over again because he was like that. And we made progress like one group at a time. We talked about groups mostly and the role they played in algebraic topology. So that's the interest that we shared. And we compared notes about all sorts of crazy groups. Now, things really developed nicely when I persuaded him to come to visit me at the University of Wisconsin in Madison, where I was on the faculty at the time. I believe it was around 1999. And I was thinking, wow, I'll have Fred all to myself for 6 months. Isn't that great, right? So, so our collaboration took off after that. In fact, we published 6 papers together. And each of those papers has a story behind it. It was an adventure and a real pleasure. You know, writing a paper with Fred was a unique experience, I must say. My collaborators I've had over the years, they're all very different in style. His style was very special and very enjoyable. So I feel privileged to have been his collaborator. He's really a mentor. I learned so much from him. And I also learned about being enthusiastic for mathematics and just keep on going, keep on going until you reach a destination that will surprise you. So I want to say here that we will definitely miss him. And in his case, I think we'll miss him forever because he's not a kind of person that you would easily forget. Okay. Now, among the papers that we wrote together, I want to highlight 3 of them, which are related to my lecture. The first one is title is Commuting Elements in Spaces of Homomorphisms. And that arose directly from our collaboration in Madison 8 years before, right? So that's for the younger people in the audience. We mathematicians can be working on the same problem for 30 years, 40 years. So don't be shy about going back to unsolved problems and trying to solve them. There are continuum in your head, and the years fly by. So in that paper, we embarked on the study or the application of techniques from homotopy theory, algebraic topology, to studying spaces of homomorphisms and representations. And this will be related to what I talked to today. And then 2 other papers, now with collaborators, Jose Manuel Gomez, who was a postdoc at UBC, and Enrique Torres Guise, who was my student at Madison, then at UBC. So the thing about Fred is that he liked to work in teams. I think I also wrote a paper, a 6-person paper with Tony and Martin and Sam and Fred and myself. Anyone else that I missed? So that was a multi-authored paper. So I really enjoyed those team efforts. There you go. We're reaching physicist levels, right? Okay. So, all right. So let me get started then. And let me see. Okay, here's the pointer. Okay, so for the purposes of this talk, I want to take a G to be a compact Lie group. And gamma is going to denote a finitely generated discrete group. And the object we want to look at, and that we looked at in the original paper with Fred and mathematician Allen, was the space of homomorphisms from gamma to G. Now, because gamma is finitely generated, we can think of that as a subspace of a product, Cartesian product of the Lie group. And so we can give it a topology as a subspace. And now these are very interesting spaces, and you'll see as we go through the talk that there are interesting connections to representation theory, homotopy theory, K-theory, bundle theory, etc. So, understanding them, of course, is an important objective in mathematics. Now, there's an associated space. So G acts on this space by conjugation. And we can consider the quotient space. And here, because G is compact Lie, we have no problem. These are like the normal quotients we do in topology. So we take rep, the quotient under the conjugation action, and we have a map. So this is like a stack situation. So there's a huge amount of information that is lost when you take this quotient. Of course, the rep is the space that representation theorists like to talk about. The HOM is a space which is richer, it's more complicated, and plays a slightly different role. So, okay, that's a fundamental object we'd like to consider. Now, so we did prove a number of interesting properties about these spaces, but you realize that even for the simplest discrete groups, these spaces are quite complicated. In particular, for example, if gamma is an amalgamated product of two groups that you know, computing the space of homomorphisms is quite complicated. So we said, well, let's look at some very easy example and see if we can't work that out. So, so the basic question here is, what can we say about the geometry and topology of the spaces of homomorphisms, hom gamma of G? And in particular, what is their homology or stable homotopy? This question raised in 2007 is still relevant. You know, it hasn't been settled. So, and now, as we said back then, well, let's look at the easy case and just get that one out of the way. The embarrassing case of a free abelian group of rank n, and see what we can say in that situation. So what happens when you plug in z to the n here, where gamma is? Then we get the space, what we call the space of commuting n tuples in G. So we can write it like this: hom zn G are the n tuples in G to the n, just as they commute pairwise. And in particular, if G is a matrix group, then we can identify this as a space of commuting matrices. So one of the nice things about Fred is that he could talk very abstractly, but he was not afraid of examples. He loved to get his hands dirty and talk about, he'd pull out strange examples and start talking about modular forms. He loved to talk about modular forms a lot. I remember that. And he'll start doing this, and then I would throw in, well, I know something about SL2Z. Oh yeah, what do you know in this and this? SL. So anyway, we always were working on very explicit examples underpinning the theory. So, so this, of course, looks very concrete. You say, well, what can you say about it? And you can certainly explain that if I look at the space of commuting matrices, that carves out some kind of variety. What can you say about its geometry? It's a very naturally posed question. So, okay, so let's see. Let's try to analyze this. So I'm going to go through some basic results about that before we get into the stable splitting piece. So suppose we take T a maximal torus with the Weyl group W. So we call that W is going to be a finite group. And one can show from basic Lie theory that if every maximal abelian subgroup in G is connected, then the representation space from 0 to the n to G is in fact homeomorphic to the nth product of the maximal torus modulo W, where W acts diagonally. So this is the generalization of the fact that G modulo the adjoint action is homeomorphic to the maximal torus modulo the Weyl group, because you know everything is covered by the conjugates of the maximal torus. So now these spaces of representations are of particular interest in geometry and physics because we can identify them with the moduli space of isomorphism classes of flat connections on principal G bundles over the n torus. So they appear in the literature in physics. Hey, there's even a paper by Witten on this topic, in the case where n is equal to 3, I believe. So they have an interest in geometry. Now, we're going to be focusing in increasingly on the unitary groups. So if G is equal to UM, then the maximal torus are these diagonal matrices. It's a torus of rank M. And the Weyl group permutes these entries. And we have the following equivalents. The representations from 0 to the n, or I should be saying Z to the n. My apologies to Canadian colleagues. The rep of Z to the n UM, you can identify it with S1 to the m n with the action of sigma m. And if you just move these around and write it this way, it's the torus, m copies of the torus, which are permuted. So it's the m symmetric product of the torus. So the m-fold symmetric product of the torus. So for the unitary groups, the Hom space is sitting on top of the symmetric product of the torus. And we obtain that by taking the quotient under the action of the unitary group. By the way, one of my co-authors is here in the audience, and he looks worried. So Simon is back there, Simon Whitchecker. So we'll get to the results soon. So now, for G with connected maximal abelian subgroups, it can be shown that this space rationally is modeled by the following orbit space. You take the flag manifold, you take the product with T to the n, you have a W action on these, because remember, the normalizer of T, when you divide by T, you get W. So the residual actual W action of W on G mod T. So you have a diagonal action here. So rationally, you have an equivalence like this. This appears in the work of Baird, who was a student here in Toronto, right? Correct? Yeah. Okay. Yeah. So, and in particular, in this case, you get here this flag manifold and this a balanced product construction over here with a torus. Now, one of the basic questions you might ask is homological stability. And here, I want to mention here a student of Fred's is Staffa here. Mentor, where's Mentor? Okay, I saw him on the list. Okay. Anyway, there's a very beautiful paper by Dan Ramras and Mentor Staffa, which is a sort of a homological stability theorem. Suppose you take the natural inclusion UR into UR plus 1. Then for k greater than 0, there exists some number S of k, such that if R is greater than S, then the inclusions induce equalities of the Betti numbers. So you have a form of homological stability for these groups. Characteristic 0. Yeah. Characteristic. Could you repeat the question? Oh, sorry, I'm supposed to say it. Sorry, I'm supposed to say he is asking whether that is in characteristic 0, and the answer is yes. Is that what I'm supposed to do?
Yep, yep.
Okay. Now, I'm going to give you some idea as to how interesting some of these objects are. And we can focus, for example, on the commuting pairs in a compact Lie group. So, oh, sorry. Oh, sorry. Going the wrong way. Oh, sorry, I'm going the wrong way. I'm giving it all out. I'm giving it away. Wrong. Okay. So if G is compact, simple, and simply connected, then pi 2 of G is equal to 0. That's a result. It goes back to Cartan, maybe. Right? And pi 3 of G is equal to Z. And we know there's a canonical three-dimensional integral cohomology class that can be realized through a group homomorphism from SU2 into G. For topologists, SU2 topologically is just a 3-sphere. Now, for these Gs, it's not hard to see that the space of commuting pairs is simply connected. And in fact, there's a canonical class which appears in dimension 2 in this case. And this is especially interesting because for G simply connected and simple, this space of representations of Z mod 2 into G, the pair, these conjugacy classes of pairs of commuting elements in G, they can be identified with a modular space of semi-stable principal bundles over an elliptic curve with structure group, the complexification of G, which is known to be a weighted projective space by work of Louis Jenga and others. So this connects to other areas of mathematics in a very interesting way. So now what we're going to see next is how, what information is contained in the map from HOM to REP, which is relevant to the Lie group. Are we doing for time? Are we okay? Okay, so okay, so now let's see. So we're going to suppose now that G is simply connected and simple, compact Lie group. Then first of all, we get that pi 2 of both the HOM space and the REP space are isomorphic to Z. And so you have a question about the degree of the map. So the question then is, what is the degree of the map in in this two-dimensional class between Hom and Ret. And now this is a theorem which is joined with Simon Whittaker and Jose Manuel Gomez from 2021, which says the following. If we look at this map, then the degree in dimension 2 is the Dinkin index, which is the lowest common multiple of the co-root integers of G. So this is an invariant associated to the compact Lie group. So even this very innocent class contains some rather interesting information. Now we can give an alternate definition of this Dinkin index, which you'll see in the next slide. So here's a table where we have the set of co-root integers and their least common multiple for the simply connected compact Lie groups. And here you have the groups, the SUM, spin, symplectic, E6, E7, E8, F4, G2. And there you have the least common multiple appearing there. Now this Dinkin index of G can also be defined as the greatest common divisor of the degrees of the map from pi3 of G to pi3 of SUN for all representations of G into SUN. That's one which topologists would find more satisfying. So anyway, this is a kind of an interesting result, which tells you that there's some information kind of built into these commuting elements, even for the pairs of commuting elements. So now you can do some computations also for pi2. And you get the following results for commuting intervals. Again, this is joint with Simon and Jose Manuel. First, there's an isomorphism. And when you see these numbers, you see that some of these numbers will appear when we talk about the stable splittings. But the pi2 of Hom z to the n SUM is n choose 2 copies of z. And this induces an isomorphism. So we were talking about stabilization before. And for the symplectic groups, you see here a big 2 torsion appearing there. So and that's the first time where we've seen some 2 torsion appearing, or some torsion. And the fact is that these spaces will have a lot of torsion. And that's what's going to make computing their homology or understanding the geometry quite complicated. So, now let me go into the more general question of a stable splitting. So the basic question, that's another thing which Fred liked to do. He liked to stably split spaces. You gave him a space and said, can we stably split it? He always asked that kind of question. And so, well, why don't we split them? Okay, Alex, let's go and split it. And they say, well, okay, let's try. And so we have a stable splitting. It's sort of a not the most refined stable splitting, but we do have a stable splitting that appeared in our paper from 2007. It was right. So let's take the commuting n-tuples in G, and let's consider there the subspace of those n-tuples where at least one coordinate is the neutral element. And by the way, a lot of the stuff which I'm talking about with compact groups, a lot of it has been generalized to non-compact groups under appropriate restrictions. Okay, but for the purposes of this talk, we just want to stay for compact Lie groups. So, and the basic result is the following. After a suspension, if I suspend the space of commuting matrices, then we have a very nice splitting theorem. It splits And here, what you have is the the commuting R tuples divided out by this subspace, where at least one coordinate is equal to 1. And then you have n choose R, and this, of course, R between 1 and n. This tells you that there's going to be a whole splattering of pieces in the stable splitting. And it tells you that maybe you want to focus on what these pieces look like. So those have some interesting geometry associated to them. Now, for people who like rep, you could also consider what happens with the space of representations. Now, we proved in the subsequent paper that this splitting can be done equivariantly. So you have it's compatible with respect to the conjugation action. And then you it allows you to do the analogous splitting for spaces of representation. And now we mentioned before that if G has connected maximal abelian subgroups, so basically we want the maximal abelian subgroups to be tori, then this rep space from Z mod n into G, so the conjugacy classes of commuting n-tuples in G is in fact can be identified with T to the n modulo the diagonal action of W. So then what you have to do, splitting this is equivalent to splitting that, and indeed with the suspension here, what you see here is a splitting. Here you have the smash product of T R times, and W is acting diagonally. So this is a very nice splitting downstairs. So the question would be, what is the splitting upstairs that afterwards restricts down to that splitting downstairs? So there are a few explicit computations done, in fact, by some people here in the audience. So let's consider SU2. When you're working in this game, like SU2 is the group you want to work on, right? Everyone likes SU2. Already SU3 is quite complicated, but okay, SU2. So it turns out that you can identify the commuting n-tuples in SU2, modulo that subspace where at least one of the entries is 1, with the following space constructed out of the real projective space. You take lambda 2 is going to be the canonical line bundle, or RP2. Sn of RP2 is the 0 section of the vector bundle, which is the sum of lambda 2 n times. And the superscript n lambda 2 denotes the Tom space of the bundle. And the answer is that is homotopic to this quotient space. Now, this result was obtained independently by Baird, Jeffrey, and Selleck, and Kraft, in independent papers. I think that's correct. So again, a very interesting result. It's telling you that, you see, these spaces have a lot of two torsions. So it's telling you that things are going to be far from torsion free. And the only prime that matters for SU2 is, of course, the prime 2. Now, for SO3, you get the following interesting result. So one of the things which is true for these spaces is that if SU2, if the space has connected maximal abelian subgroups, if all its maximal abelian subgroups are connected, then the Helm space itself is path connected. However, if that's not true, there's no reason why the Helm space should be path connected. So in particular for SO3, the Helm spaces are not path connected. So you have some other components which appear there. So that's where this funny index here is appearing here. So if I take SO3 and look at the commuting n-tuples and divide out by this space Sn, then you get this Tom space over RP2, and then you get a bunch of copies of the 3-sphere modulo Q8, where Q8 is the quaternion group. And this index is, yes, 3 to the n minus 1 minus 1 over 2. These number of components were computed by a student of mine. His name was, what was his name? Rojo. Yeah, his last name was Rojo. Rojo. Yeah, that was his name. And it was a nice thesis where he computed the space of components, the Helm spaces for the special orthogonal groups. So, so it's telling you that you have some 2 torsion there, which is going to be rather complex. Okay. So that stable splitting, the one Fred and I gave, holds without inverting primes. But with the exception of the trivial cases and the cases G equals SU2 and G equals SO3, the stable summons have not been identified geometrically. And so we can say, well, hey, if you've read my paper with Fred, can you please work out what these pieces are, right? The Helm over the S's. And what is the geometry? What can you say about them? Do you have some bright idea for computing them? So we get to the real topic of the talk, which is the special case when G is equal to UM, a unitary group. And in that case, it turns out that the commuting matrices, commuting unitary groups, have some special features that will allow us to understand the pieces in the previous splitting, but modulo torsion. So the splitting we get, we're going to have to invert primes, so a number of primes. In fact, m factorial, all the primes that appear in m factorial. And the key ingredient, new ingredient here, is that the unitary groups themselves admit a beautiful stable splitting. So here, we have to go back into the ancient era before my PhD. Yeah? And there's a very nice result due to Haynes-Miller from that era, the 80s. And Haynes-Miller proved that if you take the unitary groups, you know, our beautiful favorite Lie groups, then they admit a stable splitting. And the ingredients there are the, you take the Grassmannian, UM mod UM minus K, and you take the Thom space of the adjoint bundle. That is the vector bundle over the Grassmannian associated with the adjoint representation of UK. So here, what you have here is the Lie algebra. That's a very beautiful result. And so then you say, well, can I put Helm here and Helmify this formula and see what I can get away with? Now, UM is torsion-free. All its homology is torsion-free, so okay, but we're going to have a bunch of torsion. So it's not going to work directly. That's why we're going to have to invert in some things. But the idea then is to use the stable splitting theory for the UM and our stable splitting for the Helm spaces. How do we put these together into some coherent formula that specializes to both of those? Okay, so the main result is going to be an analogous stable splitting for the space of commuting entuples in UM. Now, as I said, the spaces of commuting matrices have torsion at primes dividing m factorial. And the presence of this torsion makes it necessary to adapt the proof to obtain this proof for the space of homomorphisms after inverting m factorial. Now, for this, we have to introduce an object which kind of generalizes the Lie algebra. It's the you know, if we're doing Helm, generalizing the group G, you know, commuting matrices, then we have to look at somehow commuting vector fields, and that's the space of commuting n-tuples in the Lie algebra mu k. So we define Cn of mu k to equal to the n tuples and uk to the n, such that the Lie bracket is equal to 0 for all these pairs. So okay, so that's the object. So this is a variety, the commuting variety associated to the Lie algebra. And it's an object of interest to, it appears in the work of the algebraists, the people who work on on spaces of representations, and there are people who work on commuting variety. And now UK acts on this Cn of UK diagonally by the adjoint representation, and it extends to the 1-point compactification. So this is a complicated object, but that's the one that's going to contain the basic information. It's one of the basic building blocks for our construction. Now we're going to have to get into some combinatorics to describe the stable splitting. And so first of all, the splitting is going to be indexed by a poset of partitions of M. We're going to denote this by P. And the elements are partitions of M into 2 to the n parts, indexed by a set of binary sequences. And given A and I, we write absolute value of A for the sum of A of I. We have that value. And here is the result. After inverting M factorial, there is a stable splitting for every integer n greater than or equal to 2. And now we have this HOM, the commuting n-tuples in UM split stably. And here you have this balanced smash product. Here you have, this is the product of unitary groups that fit in to UM from the partition that you have. And here you have smashes products of these commuting varieties for the associated Lie algebra. So that's the, now what are these stable summands? They are Thom-like spaces for bundles of commuting varieties. And these commuting varieties are irreducible. And the bundles that appear are not vector bundles, rather bundles of infinite subspace arrangements. So rather complicated combinatorics associated to them. So that's the stable splitting. And let me see how it relates to the other splitting. Now, so if you saw the splitting which you gave in the theorem with Fred, these were the elements in the splitting, right? And it turns out that they, in fact, can be split under this approach. So there is a stable equivalence after inverting M factorial, where all you have to do is restrict to a certain subset of P to recover this piece of the splitting. So it breaks up, these break up into little pieces there that give you the whole picture. So now where does this kind of splitting come from? Well, if we have time at the end, we'll talk about that. But the point here, I mean, what is the motivation for, let me see if I, yeah, sorry, getting ahead of myself. The idea of a stable splitting for me is to understand the homology, right? Because the stable splitting is a very efficient way of capturing the homology of a space. So if you know the stable splitting of a space, then you can read off the homology. Now, some homologists or cohomologists just like to compute. They say, compute mindlessly the cohomology. They used to say, we computed the cohomology of groups mindlessly. I was once accused of that. Perhaps true. So people just like to compute. If it's there, compute its cohomology. Right? So so there's a lot of work trying to compute the cohomology of spaces of commuting elements and trying to understand what the different pieces that go into it are. Okay, so that's a very important underlying motivation in philosophy here. So we're going to tie that in. You'll see in a little bit. So now the stable splitting is modeled on a filtration of UM in which the top filtration quotient is precisely this compactification of the algebra. So our splitting is obtained is a filtration with the top filtration quotient is this Cn of UM plus. So and now the next result is kind of like pinpointing why we know that the primes must be inverted for the top filtration quotient to split off stably. And this uses a Steenrod operation. So the result that we prove is that if P is a prime and N is any integer, then this projection does not have a stable section of the homotopy at the prime. So there's a problem at the prime P for UP in this top element that you have there. So because for a long time, it was a hope that this stable splitting might hold not just rationally, but more generally, that those pieces would in fact be filling up the homology of the space. Now this result tells us, no, it's not going to work. So you're going to have to write a paper where you invert primes, which is, some people don't like that.
Sorry. I think Fred didn't like that necessarily. He was willing to do it though.
So we understand that there's a problem with the splitting at particular primes. And that gets you, of course, into the issue of torsion, which appears in these spaces. So let's see an example, a calculation. See, for U2, a nice baby case. Here are the stable summands for the commuting pairs in U2. So they're indexed by, using our partition, this set with 4 elements. And we have these parts listed in the columns. So you see here, when you go through them, S0, okay, no surprises. S4, here we're nice torsion free. But here you get C2 of U2, and that has S4 and the fourfold suspension of RP2. That's where 2 torsion is appearing. Remember that for U2, we only care about 2 torsion, right? Because n factorial is 2 in this case. And in the other ones, here we have S1 wedge S3, S1 wedge S3, S2 wedge S4, wedge S4, S3 wedge S5, S3 wedge S5. So you've recognized all the pieces. So what we know is that this guy here is not going to be splitting off using that map at the top level. So our humble statement then is just away from 2, that this Hom space will be stably homotopy equivalent to this wedge of spheres. You get 2 1 spheres, 2 2 spheres, 4 3 spheres, 5 4 spheres, and 2 5 spheres over here. So of course, try to make it explicit for other UMs. I think that's where you'd have to use the artificial intelligence, right? Have you tried your artificial intelligence doing group cohomology? I did do a computation. They can do some of it, by the way. Huh? Some of the quaternion group and things like that. Anyway, it's an interesting problem to use AI for some of these computations. But, all right. For the symplectic groups that also apply. Here you have to invert more to the M factorial. And this has to do, of course, with the Weil group and things like that. So you get an analogous decomposition for the symplectic groups. Now, we'd like to tie this in to the homology. So going back to what I was saying, a motivation for proving the stable splitting lies in the effort of computing the homology of these commuting antiples, which we still don't have a general computation. Now, of course, the homology of these commuting varieties is more tractable. It's a nice, well-structured algebraic object, even though computations are still difficult. And but inverting n factorial kills all the torsion. But the question is whether or not it still holds at the level of integral homology. So from all the calculations we know, the terms which appear in the stable splitting, in fact, fill up the homology. So you can pose then the following question. Does the homology, the integral homology of this basic union antiples, is it captured by the homology of the pieces in the stable splitting? And that's kind of a difficult question, kind of wrestle with that. And of course, that was kind of our motivation for the homology computation. And this seems related to the Synod splitting of the homology of symmetric products, because we know that when you divide out by the action of UM, you get a symmetric smash product of spheres, right? And as we mentioned before, a key step in the proof of the fact that this does not have a stable section of the homotopy at the prime P is a comparison with symmetric particle spheres. So it goes back to old classic stuff from, wow, 50s, 60s. Okay. So, anyway, that's an interesting thing to think about. Caveat. Now, as a final remark on homology computations, we do want to record what the contribution from this top piece, Tn of UP is, when P is a prime and N bigger than 2 is even. So we also put that in our paper. So for every prime P and every even integer N greater than or equal to 4, the mod P Poincare series, and now these are Betty numbers mod P, is given by the following polynomial. Now, this result is based on a recent computation due to Guerra and Santani Eliana. He was my student too, Santani. He graduated, I believe, in 2023. Yeah. So they computed the multi-cohomology of the unordered complete flag manifold UP and UP of P. So it was curious. Everyone knows UN mod the maximum torus, you get the flag manifold. But no one had computed the quotient under the full normalizer. And they were able to use some techniques from, what's his name? Dev Singha has some techniques for basically using infinite loop space machine to compute the, you kind of do them all kind of in the limit and the infinite one, and then bring things down to appropriate P. So it's a very interesting computation. And we know that the homology of these guys always appears in the calculations of the homology of the commuting entropy. So that's a very important piece in what we're doing. Now, well, okay, I'll keep on going until they stop me. But okay, now I'll just give you an idea of the filtration and the proof, not in huge detail, but I guess the slides are available, will be available, and the paper is posted on the archive and wherever you want to find it. So, so let's take, so I'll give you some idea what the filtration is. Take the maximal torus of the diagonal matrices. Now there's an action of there. It acts on each of the coordinates by conjugation, and an action of the normalizer on this quotient, again, diagonal. And the map is invariant under this action, so it descends to a map here of the balanced product into the Helm space. And that's a very, very influential map. Because if you look, then if you divide out, if you look at this space here, modulo normalizer, then you can write it as the flag manifold and this balanced product modulo sigma m, where this is just the Weil group and it's permitting the function. So then a filtration of this space can be constructed by starting with a sigma m invariant filtration of Tn and pushing it forward via the map phi. And the filtration of Tn, which we shall consider then, is indexed over a poset of partitions of M, which we'll describe next very briefly. This time is running out. Okay, remember we took this binary sequences of length n, and then we looked at these I-indexed ordered integer partitions. And here are the form we saw in our table where these guys came up. Okay, that's the basic condition that we have. Okay, now here's the kind of the basic combinatorics you need. You take this ordered by the lexicographic order, in which this is the smallest element and the string of ones is the largest element. And to each partition, you associate an m by n matrix, m lambda, with entries in 0, 1, defined by blocks in the following way. In the first lambda 0, 0, 0 rows of m lambda, you put the row 0, 0, 0. Subsequently, we define the next one to be equal, well, you put in a 1, and you continue this way using the order in I until you reach the last with 1, 1, 1. And these are defined to be equal, the thing which is filled up with 1. And now we have this assignment. And if you use these matrices, you can define a partial order on P And given lambda and mu, you can declare mu to be less or equal to lambda if, after suitable permutations of rows, the matrix M mu is obtained from M lambda by replacing some entries that are equal to 1 with a 0. Okay, probably not going to pick it up here in this 30 seconds, but it gives them an idea that it's a fairly logical combinatorial construction. And now you give it a topology where the closed sets are generated by this sub-basis of which you can read there. And you have the subscript less than or equal to lambda. Here are the mu such that mu is less than or equal to lambda. And now to filter Tn, you define a map psi from Tn to P, where an element x and Tn can be viewed as a matrix of size n times n with entries in S1. Now the key thing is that T to the n has Mn coordinates, right? This is a key observation in all of this. So, and the while group permutes the rows. So you see there, to each row of x, we assign a binary sequence by setting these, prescribing these values. And we let lambda a be the number of these, such that the sequence of xi is equal to a. And you set psi t of x to be equal to this sequence. Briefly stated. And now you can define the filtration in Tn, f lambda of Tn. Well, it's the inverse image of P less than or equal to lambda. Now this is closed, that map is continuous. The filtration defined by psi t refines the fat wedge filtration of Tn, which is a key fact, which is used in these splitting. And the quotient by the conjugation action is homeomorphic to the quotient by a symmetric group. And in fact, therefore, this one factors through that orbit space. And now if we let psi from Hom Zn um into P be the composition with C psi bar, you get the desired map to P. So then we have a map from Hom into P. And then we can, we're in business. Now, what about the splitting for UM? Well, if n is equal to 1, then the filtration induced by psi is given by this, the G in UM, such as the dimension of the kernel of G minus 1 is greater than or equal to M minus K. And that was the filtration used in the paper by Haynes Miller. And if you take the map of posets defined here, such that the sum is equal to 0, then this is equal to the n tuples such that at least n minus k of the GI are equal to 1. And that was the filtration used in the paper with Fred. So this interpolates between the two filtrations. So now you can see where we're going. So this gives you a partition of the Hom space into strata. Now you consider this group here. We've talked about this before. It's a suburb of UM, just a product here. And then the key thing is you identify these strata with these balanced products over the where you have these commuting varieties. And now if we let f lambda of Hom 0 to the n um equal to the inverse image here, as we did before in the TNs, you get a filtration then induced by psi. And the key facts here that imply the splitting result is that the quotients f lambda modulo f less than lambda are precisely these terms. And the next result, that after inverting all the primes p less than or equal to this number here, this quotient map collapsing this subspace admits a stable section up to homotopy. So then working inductively, you get a stable splitting of your Hom space after inverting the appropriate prime. So and the S which you need to obtain the splitting in the paper with Fred, you take the subspace defined by the lambdas in P, such that the sum is different from zeros. And you can observe that this strata then avoids this Sn subspace. And in fact, there's a stable equivalence here. So just restricting to that subset of P. So anyway, that's sort of a sketch. Obviously, you'll have to look at the detail. But the question, though, as to whether we can fill up all the homology or not is it's an open question and interesting to try to do some explicit computations to verify that or not. So I think I'll stop here. Thank you.